So we've spent a decent amount of time talking about the Lagrangian function and its uses and the ideas behind it. So the Lagrangian is a function of the generalized coordinates. I'm going to use q. Q is our generalized coordinate. It's not necessarily a rectangular coordinate. So our generalized coordinate are generalized velocities, right? The time derivatives of these things. And then also the time. It can be a function of these three things. And there could be more than one generalized coordinate, and maybe you want to use a subscript to keep track of all of them, but we haven't really been doing that, so we're just pretending it's in one coordinate right now. One generalized coordinate. But anyway, this is the Lagrangian, a function of these three things. And a related function, which is the whole focus of this video, is the Hamiltonian, which we'll write as h. And the Hamiltonian is similar to the Lagrangian, also based on the principle of least action. But it is a function of a different variable. So it's still the generalized coordinate here, but instead of the generalized velocity, it's the generalized momentum. So I'll write p here, and p just means generalized momentum, even though p is normal momentum as well. And then it's also a function of time. So the Lagrangian is a function of the generalized velocity, while the Hamiltonian is a function of the generalized momentum. And I know what you're thinking. You might be thinking, at least, that what's the big deal here, right? Momentum is just the velocity times the mass, right? Well, that's true in rectangular coordinates, but in generalized coordinates, that isn't necessarily true. So if we write down the Euler-Lagrange formula, maybe just, and I'll write it in terms of q. So dl dq, dl dq minus d dt, whoops, that's not how you write a time derivative, d dt of the partial of L with respect to q dot, right? This is our generalized velocity, equals 0. Right, so we touched on this a bit in the video about the method of undetermined multipliers, but this, we can think of this thing as a generalized force, right? If we put this in rectangular coordinates, this actually ends up being the force. So generalized force, generalized force, generalized force. This is an n. Generalized force, and this is the generalized momentum, right? Force is the rate of change, ddt, of the momentum. So if we put in rectangular coordinates, this chunk here ends up being the momentum. So in general, it's the generalized momentum. Generalized momentum. Generalized momentum. Okay. All right. So we said that mass times velocity is momentum, and that's only true in rectangular coordinates. If we go to, say, rotational coordinates, an example you might be used to thinking about is that if our generalized coordinate is theta, then our generalized velocity will be theta dot. So this is our coordinate, and then this is our velocity or speed, since it's only one variable. And then our generalized momentum, right? If we just said generalized momentum is just the mass times this generalized velocity, we would just write that our momentum, our generalized momentum, is m theta dot. Generalized momentum. Generalized momentum, right? Actually, this isn't true. We know that's not true. So generalized momentum, this would be the angular momentum. But we know that m times theta dot isn't the generalized momentum. It's actually the moment of inertia times the generalized velocity. So this thing here, this moment of inertia, it contains all kinds of stuff about the problem, right? And there's a dot here. So we can't just say that these things are trivially related to each other. These two things are not necessarily just related by a constant. So these two things actually do have a significant difference between them. And it might even be more complicated for other things other than just rotation that we're used to thinking about. This isn't simply the mass. This has a radius and maybe like a constant factor in it, probably a squared radius. But anyway, so now that we know that these things are different, why is it more useful to have momentum? Why is momentum more useful? And the answer is that it's mostly useful for things outside of classical mechanics. Generally, to find the generalized momentum, you have to use the Lagrangian anyway, unless it's something simple like the mass times the velocity. So generally, it's not that much more useful for classical mechanics, but for things like quantum mechanics, especially quantum mechanics, as well as relativity, momentum is much more useful. Relativity. So the difference between these things, just to say it one more time, is that the Hamiltonian is a function of the momentum, the generalized momentum, while the Lagrangian is a function of the generalized velocity. So in simple cases, these things sort of seem to be almost the same thing, but in more complicated cases, such as even rotational motion, where it's not just the mass times the generalized coordinate, or in quantum mechanics, where things, the ideas such as velocity, aren't quite the same in relativity and quantum mechanics. This concept of using momentum to write down our equations is actually much more useful.